sisters, we know about stars.
Really, you do?
Yeah.
What can you guys tell us?
Come on.
This is how nuclear fusion works. Deuterium and tritium, two isotopes of hydrogen, are forced together to create one big nucleus. This nucleus gives off an immense amount of energy because the deuterium and the tritium are being forced together by the heat that is in the core of the star.
The energy given off is exothermic and is released in the form of gamma rays. These gamma rays can make a long journey through the star, being absorbed and then re-emitted from atom to atom. This journey slows down the energy of the gamma rays and makes the energy visible in the form of light.
Another product that is given off in the reaction is helium-4, which is the two helium atoms formed from the two hydrogen isotopes.
Wow, that's really cool. I didn't know that.
What happens after nuclear fusion? Does the hydrogen keep regenerating?
Well, you see, stars can emit energy as long as they have hydrogen fuel in their core. Once this hydrogen runs out, the fusion reactions shut down and the star begins to shrink and cool. Some stars will simply turn into white dwarfs, while more massive stars will be able to continue their fusion process using helium and even heavier elements.
In today's world, we can relate the nuclear fusion to new inventions that are incorporating the nuclear fusion process. Let's go and meet Brian McGowan, director of the Lawrence National Ignition Facility, where scientists are currently developing the world's largest laser. We are here with Dr. Brian McGowan, who helped develop the laser. So, Dr. McGowan, tell us about this new laser you've created.
Here at the NIF, we've invented a laser, which happens to be the size of 3 football fields to develop a carbon-free, limitless fusion energy.
How does it work?
I'm glad you asked. How it works is that a beam of concentrated light charges up by bouncing back and forth over the distance of a mile, and it is then split into 192 beams, which are concentrated on a tiny spot of deuterium and tritium called a hadron.
If you remember from before, deuterium and tritium are reactive isotopes of hydrogen that can be extracted from seawater.
Anyway, when the laser is fired, the fusion reaction will be more than 100 million degrees, hotter than the sun, and exert more than 100 billion atmospheres of pressure. We hope that the process will undergo fusion at its core. In other words, we are imitating the nuclear fusion process in stars to create the necessary energy needed for an unpolluted, carbon-free source.
I didn't know nuclear fusion could work like that. It's really cool.
That it is.
Look, it's Hans Bethe, coming through the time machine from 1939.
Guten Tag!
Dr. Bethe, tell us how you discovered nuclear fusion in stars.
I'd be delighted. The first thing that began my research was when I learned valuable information from my old friends Robert Atkinson and Fritz Hauptmanns. They used the measured masses of low-mass elements and applied Einstein's E equals mc squared to predict that large amounts of energy could be released by fusing small nuclei together. Some years later, I heard from my friend Mark Oliphant, who told me that he discovered helium-3 and tritium, and that heavy hydrogen nuclei could be made to react with each other. I conducted countless experiments based on my knowledge of nuclear physics, and finally concluded that the nuclear fusion is the reaction that happens in stars and similarly in the sun.
I was wondering, are there any other forces that drive nuclear fusion?
Well, actually, there is one that I can explain. It's called cosmic radiation. Stars can form because of this radiation in space.
The radiation in space provides nuclear fusion in the sun and stars with the nuclei of hydrogen and other elements. These elements are in the form of cosmic rays, which are fast-moving particles of matter.
The cosmic rays can travel through space at hundreds of thousands of kilometers per second. Some electrons in the cosmic rays travel at nearly the speed of light. Cosmic rays are also responsible for the continuous production of a number of unstable isotopes in the Earth's atmosphere.
I thought radiation was a bad thing. If it's in space, does that mean it's here on Earth?
There are many ways radiation can get into our atmosphere, but the two most troubling ones have to do with electrical power blackouts and human radiation exposure. When cosmic ray particles enter the Earth's atmosphere, they collide with molecules, mainly oxygen and nitrogen, to produce a flood of lighter particles called an air shower. This is pretty much a shower of radiation particles flooding the atmosphere.
When do we have to worry about space radiation hazards?
Basically, these air showers are the problem because they penetrate Earth's magnetic field. When a solar wind hits the Earth's magnetic field, electrons and protons inside the field are accelerated into currents that flow along the very thin magnetic field lines and meet on the south and north pole. Soon after this, a satellite can start to experience problems as energetic particles pass through them and begin to disrupt their operation.
What she's trying to say is that these hazards are only a problem for satellites and those exploring in space and spacecrafts. The cosmic rays can easily seep through anything in its path. A week in space's cosmic ray environment will shorten your life expectancy by a day, as well as increase your risk of cancer.
There's no way I'm going into space.
You're a cracker.
So what have you guys learned about stars?
Well, I know a lot about nuclear fusion.
Yeah, like how nuclear fusion occurs when two hydrogen isotopes are forced together by the heat of the star's core to create a larger nucleus.
The products of nuclear fusion are gamma rays and helium-4.
We also learned a lot about how nuclear fusion is being used today and how it was discovered.
Yeah, like that cool laser invented by Brian McGowan.
And how it mimics nuclear fusion in stars to create a limitless amount of carbon-free nuclear energy.
Also about Hans Bethe and how he came up with the idea of fusion in the sun and stars.
Yeah, it was also really cool how cosmic radiation starts the process of nuclear fusion.
Stars are interesting.
Thanks, Cosmic Sisters.
No problem.
How do stars shine? Stars shine because of the gamma rays that are produced during nuclear fusion. Normally the energy of gamma rays would be too high to see by the human eye, but since the gamma rays have to travel through the atoms in a star, the energy is slowed down to a visible spectrum in the form of light.
How do cosmic radiation and nuclear fusion relate? Cosmic radiation is what supplies the hydrogen nuclei, allowing the nuclear fusion to start. The nuclei of hydrogen are present in cosmic rays that float around in space.
What's a white dwarf? Most people think of white dwarfs as dead stars. This is somewhat true, but before a dead star becomes a white dwarf, it becomes a red giant. A star becomes a red giant when the star runs out of hydrogen to keep its life going. Then, the red giant sheds off layers, and the remaining core is the white dwarf. The white dwarf gives off a lot of heat, but this is just leftover heat from the star's life. The white dwarf is no longer producing any heat. Once all the heat runs out, the white dwarf becomes a black dwarf. A black dwarf hasn't come into existence yet because white dwarfs take an immense amount of time to cool off, and there hasn't been enough time in existence for this to happen.
What will happen when the sun explodes? The sun is not large enough to explode. Instead, it will become a white dwarf as explained before.